Alright, welcome everybody. So today I'm going to talk to you about some of the tools that we use to measure, and detect different compounds in organic chemistry. The idea behind this is to give you some insight into some of the machinery and the techniques that scientists use pretty much every day when they discover a new compound, or if they have a compound and they want to confirm its identity. And the three techniques that I'm going to be talking to you about are infrared spectroscopy, NMR, nuclear magnetic resonance, which you also might know as MRI, and then mass spectrometry. So, it's short mass spec, IR spec. That's what they call it. So, to give you a little bit of background, some review, spectroscopy, it's the main method that we're going to use for probing what a molecule looks like and what an atom looks like. And so you're used to seeing this in terms of when we do an atomic spectra. And so this is showing you how a star gives off certain, like spectra based on what its electron configuration is. And when we look at the electromagnetic spectrum, we're generally using wavelengths from all over it. So radio waves and microwaves, those are less powerful forms of radiation, if you remember this from when we did the atomic structure unit. And then we have our infrared, or IR spectroscopy, and then our visible and ultraviolet light, which is what we're using to, excite atoms when we look at electron configurations. Now, if you remember the energy of this radiation, it is equal to Planck's constant times the frequency. And you just took your midterm, so maybe you use this on the midterm in one of the problems, although I don't think I had one exactly like this. But the idea is that the higher the frequency of the light, the more energy that light contains. This is based on light as a particle as being a photon. And so you can see the typical frequencies for different types of radiation that can be given off. And we have this infrared light here, which is one of the less powerful forms compared to ultraviolet, which is more powerful. And what you're going to see with the infrared spectroscopy when we talk about it today, we're going to talk about how it gets the molecules' bonds to wiggle or to vibrate or to stretch. And that form where you stretch it and you get the bonds to wiggle is able to be detected. And we can tell what type of bonds they are by comparing it to known bonds. So when we do an IR spectroscopy, and that's the first technique that we're going to talk about, that's what this video is going to go into, we use something called a wave number. Basically, a wave number is just 1 over the wavelength. And so if we know the wavelength, if we take 1 over the wavelength, we can figure out what its wave number is. And so they do a calculation down here, and they show you that the wave number for infrared light with a frequency of 3 times 10 to the 13th hertz would be 1,000 centimeters negative 1. Notice the unit centimeters negative 1, that refers that it's 1 over the wavelength, as opposed to the wavelength being in centimeters. Now, when we look at the different types of electromagnetic radiation that we can use, again today we're going to focus on infrared, but you can also use radio waves as well, and that's what they use for NMR. And this gives you an idea of what certain atoms, what environment they're in, and that may seem like a loose term, the environment of the atom, but you'll see in the technique it allows us to see, how many hydrogens there are, what the hydrogen is connected to, and how that actually works. Just going to pause this for 1 second. So when we have infrared spectroscopy, that's really going to cause the bonds to stretch or to bend, and it gives us information about the bonds in a molecule. For example, is the carbon double bonded to an oxygen? Is it double bonded to another carbon? And you'll see what these graphs look like. So here's some more information about the different ranges of the regions of the electromagnetic spectrum. So you have your UV invisible, where you can have these transitions between for electrons, and you could tell ground state, excited state, and electron configurations. We have X-rays that can be used to actually, cause electrons to be ionized. We can also tell the structure of crystals from using X-rays and X-ray crystallography, and then gamma radiation as well. And this can be used to cause actual energy changes in the nuclei. So, if you remember back, we talked about absorption and emission spectrum. And absorption is where we have these, black lines where light is being absorbed, and we can see that here. And you'll see that they correspond directly to the emission spectrum. And you're going to see this comes up with infrared spectroscopy too. It doesn't look like this, it's not colorful, but you have a graph where you have an absorption spectra of light, and that tells you what kind of bonds are present. So what does an IR spec look like? Well, here you go. Here's a graph of a molecule that has different functional groups in it. And so you can see there's the C double bonded O. And so they'll call this a peak right here. And it has a specific region where it shows up. So, on the graph here, it shows up around 1600, 1700, between 17 and 1800. We get this deep sort of valley there. We also have a carbon-hydrogen bond over here. And this carbon-hydrogen bond, this shows up around 3000. Now, what chemists do with this is they have a sample and they run it through one of these machines that generates an IR spec. And then they compare it to a book, or now they use computer programs to compare it to known molecules. They analyze the spectra. Now you could have a very complicated molecule. This is normally kind of like the first step in what a scientist is doing. This doesn't tell them everything about the molecule unless they had some idea of what it looked like, but this gives them an idea of what kind of bonds are present. Scientists will use this in conjunction with other techniques that you'll see, like NMR and mass spectroscopy. So how does this work? Well, the bonds are like springs. There's a vibration to them, and depending on how strong the bond is and how heavy the atoms are that are connected, they are going to have vibrations at different frequencies. If you're a lighter atom, you're going to have a higher frequency vibration. If you have multiple bonds, you're going to vibrate at higher frequency. So they'll use this infrared light to get molecules excited. And this will cause the bond to stretch or bend. It's not powerful enough to break the bond, but it causes the bonds to wiggle, to bend, and this will cause there to be some kind of absorption of the infrared light that you can see on that graph. Now we have the bending, the stretching, where you have asymmetrical versus symmetrical, and depending on what's happening will depend on whether or not you will actually see a reading. It's called IR active, IR inactive. So not all of the vibrations that you will see are going to actually absorb infrared. There has to be some kind of change in the bond polarity. And as this vibration occurs, if there's a change in the bond polarity, if there's a dipole moment that can form or be exaggerated, then you'll have this absorption of IR light. If you have a diatomic molecule, you're not going to see this. And so they're using this in organic compounds that either have a very minimal polarity that can be exaggerated or bonds that are polar, like a C double bonded O. So here's showing you some of the different vibrations that can take place in different molecules, depending on if there's a symmetrical or asymmetrical stretching or bending. if it will be active or inactive. If you have a nonpolar molecule, depending on the stretching that could take place, if you have a symmetrical stretching for something that's already nonpolar, it won't be active. If something's polar and you have this symmetrical stretching, you'll still be considered IR active. Now you don't need to really know about the machine itself, but this just gives you a schematic of what the machine looks like. So what is it that you need to be able to do? Well, you need to be able to match up based on what type of bond is there, what you actually would see. So what they normally look at is a region outside what's known as the fingerprint region. The fingerprint region, there's a lot of overlap between the absorptions, and so you don't really get a clearer reading. So things like those halogen or alkanes, you don't really get a good reading. But then as you get into these other types of molecules, you'll see that you get some very strong and very broad, like or large absorption areas. So there is actually, this is given to you in your data booklet. And so here is the data booklet that you get. And this comes in your IB data booklet. And they'll give you a molecule and they'll give you some hints about it. And generally how the problems work is they start off where they ask you, they start off with some IR data and some hint about the molecule. And they ask you to identify parts of the molecule that could be present in the IR data based on the bonds. So they could give you a hint about that it's an alkyne, and you could see that there is, some kind of C triple bond C by absorption in this region of the IR spectra. Same way you could see that there's a carboxylic acid. They have this strong and very broad, meaning that it will be a very deep valley that you'll see, and it'll be wide. You could also have, something like an aldehyde or a ketone or a carboxylic acid again, where you have a different peak over here where it's not as broad, but there's a strong sort of indentation. So, when I look at one of these IR spectra, and we'll do that tomorrow, we'll spend time in class analyzing it, we'll really look at where are the peaks. Now, you can't exactly, tell 100% what the molecule is by using this technique. Let me just be clear about that. I know I've said that. And I'll say it to you again, you can't identify fully. But you can get an idea of what the functional groups are, and you can narrow down your scope of searching for the molecule. What we'll talk about next time, we'll talk about something called index of hydrogen deficiency. And we will talk about the equation and the equation that's used to figure out how many double bonds there are. Hydrogen deficiency, it allows you to tell if a molecule is unsaturated, if it's deficient of hydrogens. And so, unfortunately, they don't give you this equation here, but they expect you to actually be able to use it. And so we'll talk about, we'll do some different molecules, and we'll see how it works. Okay, so I'm going to stop here. Oh, wait a second. I'm not going to stop here. Let's just look at this one spectra here to kind of get an idea and match it up. So here's ethanol. And so they're showing you a CH stretch. And if we go back to our data booklet and we look at our CH stretch here, okay, it says alkanes, alkenes, and arenes around 28 to 3090. 2850 to 3090, and here it is. Here's our CH stretch. And then we have our OH stretch, and we're looking for the OH for alcohols. And notice the OH for alcohols here, if we change the color, the OH for alcohols here is about 3200. If it was a carboxylic acid, that OH would be by the 2500 area, but it's not. And so there it is, right at 3391. If we go back again, we're right there between 3200 and 3600. And so this gives us a known. If we were given ethanol and we did an IR spec on it, we would have something that looked like this, and then we would be comparing it to known molecules. Okay, so here's another IR spec, and you can take a look at this and see and compare it, and we could talk about this one in class tomorrow. So thanks for watching, and we'll discuss some IR spec tomorrow in class.